So what you're looking at right now is a bacterial weapon. Technically, this is a defense platform used to fight off viral infections already raging inside bacteria. Regardless, the way this little bundle of protein and RNA defends against phage intrusion is so wild. To the point that when the paper describing the discovery of this complex, called DRT3, hit the PR wire earlier this month, my little corner of the internet basically exploded with takes talking about how one of the central quote-unquote rules in biology had been violated. And let's kill the clickbait immediately. That is not what's happening here. But if you let me take you through the context real quick, you'll see that what DRT3 does is actually far cooler. In a world where it seemed like you could only build DNA using another DNA strand or RNA, DRT3 sets off a kind of DNA bomb, assembling long, nonsense fibers of DNA using two little bits of protein as part of its template. This machine is a complete mind blow and an excellent introduction into the world of phage defense. In this video, let's explore how a DNA grenade can help a bacterial community fend off the viral horde. No war but the phage war, folks. Let's explore why. And hey, welcome back to Clockwork, a show about the molecular foundations of life. Subscribe here so you don't miss new episodes as we explore the base mechanics that root you to the world. And make sure you check us out over at patreon.com/clockworkshow to see our perks like monthly sticker packs and great molecular paper crafts. But let's jump into the thick of it. For billions of years, there has been one endless conflict raging across our whole biosphere between bacteria and parasitic bacteriophages like these. This war is brutal, with some estimates suggesting that a full 25% of all bacterial biomass is wiped out by phages every day. Now, of course, that number is hard to verify, but the important thing to keep in mind here is that there is a tremendous amount of pressure for bacteria of all kinds to defend against phage infection no matter the cost. And that's been one of the cooler lines of research for the last 20 years. Turns out, despite being unicellular, bacteria have their own kind of internal immune systems for keeping these phages at bay. Bacteriophages reproduce by injecting their genetic material, be it DNA or RNA depending on the specific virus, into host prokaryotes and hijacking their cellular machinery to build more phages. So bacteria have all sorts of defenses aimed at targeting that viral DNA before it can complete that hijacking process. You've probably heard about the most famous of these defense platforms, CRISPR-RNA and its Cas9 protein partner. Bacteria store viral DNA sequences inside that CRISPR RNA and use it to direct the Cas9 protein to cut down viral DNA before it can do any damage. And scientists have re-engineered this system to empower a new age of DNA editing in the past decade. It's kind of been one of the biggest deals in biology, honestly. But there's actually tons of different kinds of CRISPR systems, and more importantly, a ton of anti-CRISPR weapons developed by viruses to regain an edge in the conflict. That's the wild thing about this phage war. Both sides are constantly pushing against each other in this kind of evolutionary arms race. And our subject today is one of the wilder defense strategies developed by bacteria. All the recent hype surrounds this complex, DRT3. And okay, this is a defense-associated reverse transcriptase. I figure we've set up the defense part of that name, so let's look at the back half of this title. Reverse transcriptases already rewrote our understanding of how life works back when they were discovered in the 70s. They use an RNA template to generate a new strand of DNA. Viruses like HIV and hepatitis B use reverse transcriptases to smuggle their RNA code into our genome when we get infected. The gist here is DRT3 is going to somehow use a DNA generating process to defend against attacks from several different classes of bacteriophages. And yes, this is a molecularly accurate rendering of a T1 bacteriophage. They really do use proteins to build these near-crystalline spaceship-looking delivery vehicles for their predatory DNA sequence. And instead of having little spaceship legs you might associate with phages, they just have this long, flexible tail that spears right into their victims' cell membranes. But back down to DRT3, let's focus on how this complex builds a DNA strand. First off, let's break this thing down. We're actually looking at a complex of multiple identical copies of a DRT3 system. If we zoom in on just one of them, a complete DRT3 module has an A and B component, as well as a critical catalytic RNA that partners up with DRT3A. This core DRT3 system joins with two other copies to form this little trimer, which then gets glued butt to butt with an identical complex to form the full DRT3 platform, which means we're working with 6 identical copies of the system. But back down to the individual module, let's look at these individual components to really suss out what's happening here. DRT3A is your classic bread and butter defensive reverse transcriptase. The protein of 3A stabilizes this non-coding RNA around the enzyme's active site so that these letters in that RNA knot can be used as a template for synthesizing a long strand of DNA that just repeats the guanine and thymine or G and T letters of the genetic code over and over again. You'll find this a lot with these defense-associated reverse transcriptases. For emergency reasons, we need to assemble a whole bunch of DNA in a whole lot of hurry, so it doesn't necessarily matter what information is being carried inside that DNA. Similar complexes will assemble DNA strands randomly or just keep spitting out one letter over and over. DRT3 is really special because it can print out a whole bunch of DNA very quickly using all 4 of the DNA letters. While 3A is using this normal RNA method to spit out a bunch of GT repeats, 3B is causing all the drama by adding a complementary AC strand with basically no help from nucleic acids of any kind. This is the mechanism that blew the molecular biology internet up earlier this month. While 3A is building a GT strand, 3B is almost magically finding a way to correctly add A's and C's in the correct sequence very quickly. And if we zoom all the way into the active site, the magic comes from these 2 segments of 3B's protein code. See, one of the things that makes DNA so amazing is just how much these individual letters want to become a polymer. Raw DNA letters are actually triphosphates, super energy-dense molecules that are eager to pop a few of these phosphates off and release a ton of energy in the process. What's wild is, and I kind of beat this fact to death, but the RNA version of these letters is adenosine triphosphate, the universal energy currency that all cells use to do basically all the chemistry of being alive. But if these letters just bump into each other in the wild, odds are the angle won't be right for them to actually join forces. A DNA assembling enzyme uses complementary DNA letters to hold our raw nucleobases at the exact right angle so they can touch, join the polymer, and then release a bunch of energy that pushes the reaction along. But every enzyme that builds DNA or RNA like this that we've seen across the whole tree of life uses complementary DNA or RNA to do that building, because complementary nucleobases have this perfect chemical attraction thanks to weak hydrogen bonds. T will only get added to a strand if there's an A to hold onto it, and G will only join if there's a C ready to help out, and vice versa. But this B module is so clever because it will use these 2 sections of protein, these 2 amino acid residues, to do that holding. When DRT3 gets activated, it creates this little perfect pocket where this glutamine amino acid pokes out 2 hydrogen bonding sites that are the exact right shape to capture an adenine letter, which will start building 3A's contribution to the DNA double helix. When adenine gets added on, it's going to shove this chain along, which will create a pocket where cytosine can use these hydrogen bonds to join the strand. It is the exact same chemistry that you get from using complementary nucleobases, but it's these proteins that are providing the hydrogen bonding sites. C gets added here, A gets added here, everything moves on, then C, then A, then C, then A. The way that these hydrogen bonding sites are spaced means that no matter what, these letters have to get added on in this sequential order. C followed by A, followed by C, followed by A, which is just incredible that just this protein can produce this repeating AC-AC sequence. And this is going to combine with GT's more vanilla process, producing a GT strand, which is complementary to that CA sequence. And so you get this slick system where 2 complementary strands of DNA are assembled at the exact same time in a way that they can find each other and zip up into a double-stranded DNA polymer. When activated, DRT3 will just keep pumping out this full nonsense repeating double strand of DNA, and in laboratory conditions this process has gone on until the thread is about 2,000 to 5,000 DNA letters long. And since DRT3 is actually in a big old complex like this, we have 6 of these long DNA threads running all over the place. And that's very cool. Awesome. We have this protein that makes a whole bunch of DNA in a special way, but I kept calling this a defense-associated reverse transcriptase. So a bunch of questions. How do we know that this is defense-associated? And how on earth can printing a bunch of DNA defend against a phage infection? And we're going to answer those questions and show off some astonishing tricks that bacteria pull to fend off the viral horde. But first, we'll need to hear from this video's sponsor, which once again is me. I loved rendering these molecularly accurate models of the T1 bacteriophage, and while they look cool on screen, they look even better in paper. That's right, folks. Once again, this video is brought to you by our incredible supporters at patreon.com/clockworkshow. I can only make animations this detailed because our patrons de-risk the effort and time it takes to make accurate animations that serve the science of molecular biology more than they serve the algorithms they're hosted on. But I'm no slouch either. Every tier over at patreon.com/clockworkshow has access to incredible physical perks. And right now, it's Phage Month for our supporters. This month, every patron is getting our bacteriophage sticker pack featuring both the T1 phage from this video and a surprisingly slick render of the more iconic T4 phage. Our Alpha Helix patrons get an additional temporary tattoo every month, and the T1 version of that looks awesome. Then, our protein level patrons are receiving this layered paper render of the T4 phage capsid, while folks at the super complex tier and above have access to this beefy 8x10-inch papercraft featuring a whole T1 phage. Thanks so much for listening. Your support is critical for pushing this channel to the next level, so check us out over at patreon.com/clockworkshow today. But for now, let's jump back into phage defense. First up, let's zero in on the more pressing question. How can DRT3's DNA bomb strategy defend against phage infection? I don't think repeating the same 4 letters over and over and over again is going to produce any usable protein, so what's happening here? Now, this is the part where things get tricky, because based on just the tests done in this paper, it's actually hard to know precisely how DRT3 fits into an antiviral response. Best guess right now is that DRT3 works like its cousin DRT9, which probably activates a similar DNA bomb strategy in order to soak up critical proteins produced by another class of bacteriophage. The team behind the paper also alluded to this, where you can make the argument that the bacteria wielding DRT3 are using DNA like a literal net or sponge to tie up and trap viral proteins. Out here in the media space, we talk a lot about how easy it is to break DNA molecules, but one of the superpowers that's made DNA kind of like the storage medium for all life is the fact that DNA is an incredibly stable polymer, provided you don't expose them to extreme forces or radiation or reactive oxygen species or whatever. So it could be strong enough to sort of gum up the works and sequester viral proteins once they've been detected. Our immune system actually uses DNA in this way. You've got white blood cells called neutrophils, which straight up blast pathogens with a sticky glob of their own DNA called a neutrophil extracellular trap, or NET. Nice. But you could also think of DRT3 as a kind of asset denial platform. Phages invade in order to steal resources from their host bacteria, and spewing out this much DNA very quickly sucks up a ton of energy and spare DNA letters, making it hard for the virus to assemble more of itself. And if that seems like a weird strategy based on what we've seen so far, keep in mind that bacteria have 2 main concerns when they find out they've been infected. First of all, 1, they're probably going to die, and 2, they're probably going to be turned into a bomb that kills all their friends nearby. Therefore, some of these antiviral responses are actually meant to completely destroy the bacteria from the inside before the phages can steal any more resources and build more phages. It is an incredible, community-oriented response that helps keep the whole species alive while sacrificing the individual, which may be surprising if you think about bacteria as selfish individuals only. And okay, that's cool, but I think we skipped a step. Why do we feel justified in giving DRT3 the defensive reverse transcriptase label? Just how do we know that this is a defense protein? And how would it interact with other defensive tools like CRISPR? For me, this highlights one of the most important contributions made by this paper. The team here managed to isolate a single phage protein, ST61, that provably activates the DRT3 system by itself. This is huge because it helps prove that DRT3 is a defense weapon, and it also demonstrates where DRT3 fits into the antiviral response. If DRT3 is set off by a phage-coded protein, that means it only activates once we've hit the point of no return, after the phage DNA has gained a foothold inside the host bacteria. I need to repeat this point because it is critical. It isn't phage DNA that activates DRT3. It is a fully synthesized phage protein. Most bacteriophages are just shoving predatory DNA sequences into their victims, so encountering a phage protein means it's already game over. CRISPR and other DNA-destroying systems are like the frontline defense for bacteria. They snip and destroy predatory DNA before it can completely take over the cell. If CRISPR can neutralize phage DNA before it gets to critical bacterial proteins, the bacteria might survive. However, if that frontline defense fails, there really isn't any turning back. This viral DNA is so good at hijacking bacterial systems that, once it starts taking over, our victim here has as little as 5 minutes to react before its metabolism is irreversibly shut down and repurposed for viral production. It's that fast. That's what makes a system like DRT3 so powerful. It is an incredibly fast defense system that sits outside the genome and can't really be stopped once the party starts. One of the more evil things some phages do is hang out and wait a little once they've basically killed off their host's metabolism. Without replication and maintenance, the bacterial DNA will degrade over time, breaking back down into raw nucleotides, which the viral machinery will just repurpose into making more viruses. But the virus can't do that if DRT3 is over here competing for those same nucleotides and effectively denying denying this phage a clear path to assembling new viruses. Still, without further study, it's hard to say precisely what making all this DNA would do to defend against phage infection. And since the whole, violating the central dogma thing is just a product of the internet hype cycle, that can leave us with a deeply unsatisfying conclusion to this video. But come on folks, you know me. Longtime clock watchers know exactly what's coming. This is always the best part of the video. Let's add some more context and see how this asset denial thing would actually play out. Get this, the PI who led this DRT3 discovery also worked with the team that 2 years ago absolutely nailed both the structure and precise job performed by one of DRT3's cousins. Let's contextualize this around a fully formed defensive response. Meet DRT2, folks. This defense platform is much smaller than DRT3, but wow, does this thing ever punch above its weight. The way that DRT2 weaponizes DNA in response to phage infection is jaw-dropping, and I have been dying to tell you about it ever since this paper dropped in 2024. So y'all, let's put this all together and see exactly how you can arrest a viral takeover even after you've passed this point of no return. Like DRT3, this is a reverse transcriptase, but when this one activates, it uses this circular RNA to continuously pump out a repeating DNA strand that kind of loops back on itself and becomes double-stranded. What's different here is that we're catalyzing a long circular RNA to encode actual repeating information. What DRT2 does is assemble a fully ready-to-produce gene out of thin air that hijacks the bacteria's own machinery to produce a recursive mRNA. This repetitive DNA code ends up being around 120 letters long. But again, they really pack a punch. Every repeat has a spot for the bacterial RNA polymerase to bind, as well as the instructions to start making a protein, the start codon. But critically, it has 0 stop instructions. Basically, RNA polymerase will get stuck on here and just keep printing out a repeating mRNA sequence, potentially endlessly. And sure enough, that mRNA is going to find its way to a ribosome and trap it in an endless open reading frame of its own. The ribosome is going to be stuck here, unable to stop building this, a completely useless little accordion protein chain that's just the same helical bundle strung together over and over again without end, until the bacteria starves to death or this long repeating nonsense protein causes fatal amounts of damage by gumming up the works nearby. So again, a circular RNA attached to a reverse transcriptase makes a repetitive sequence of DNA, which makes an endlessly repetitive mRNA, which makes an endlessly repetitive nonsense protein. By setting off this little chain reaction, DRT2 has effectively halted the bacteria's metabolism on its own very quickly, whether by trapping all of the bacteria's RNA polymerases and ribosomes in endless reading frames, or by this useless protein getting tangled up in the rest of the bacteria's metabolic machinery. No matter what, DRT2 halts everything much faster than the invading viral DNA can. Again, DRT2 exists as a kind of self-destruct system bacteria use to protect their community when they realize they're about to get zombified by a phage infection. This is such a beautiful Uno reverse card in my view. I mean, this bacteria is effectively saying, oh hey, you want to steal my stuff and use it to kill my friends? Joke's on you, loser. I'll steal my own stuff and build a bomb out of nonsense. Good luck breaking this accordion cable thing down into the base amino acids you need to build more phages, loser. It's like the Philly sports fan response to phage infection. I'm serious, this might be one of my favorite things I've learned about in bacteriology. DRT2 races to destroy this bacteria's metabolism by just endlessly repeating the same 120-word code over and over. And since that code repeats the start codon and RNA polymerase binding site over and over again, it's possible that multiple polymerases and ribosomes are getting stuck on these DRT2 DNA repeats, which would rapidly soak up all these bacterial resources before the viral DNA could reach a critical mass. And really the only super minor issue with this DRT2 paper is how the team here couldn't find a specific trigger that activates this nonsense cascade after phage infection. But that's just another detail that makes the DRT3 paper even cooler, since the team here managed to isolate this single phage protein that provably sets DRT3 off. So despite the fact that we instantly killed that clickbait about the central dogma of molecular biology being violated today, we instead saw how bacteria can cleverly hide these unstoppable DNA bombs in their cytoplasm as a last line of defense against phage infection, which for me is a way cooler payoff. This is incredible to me, because why should it matter to a single bacteria if its community gets infected if it is already guaranteed to die? Game's over for them already, it shouldn't matter, right? But these defensive reverse transcriptases work because they help limit the spread of phages and keep the community alive. Systems like DRT3 and DRT2 floored me when I first learned about them. We are only able to be multicellular because our individual cells will sacrifice themselves without question if things start to go wrong. It's a process called apoptosis, and it is critical for keeping the whole multicellular operation alive. And to me, it is so incredible to see other systems that work like that kind of altruism operating at the single cell level. The way we've uncovered the mechanics of our biochemical world created a narrative that was very focused on selfish actions and individualistic survival in the mid to late 20th century. Since then, we've uncovered more and more about how community-based life is at all levels. If bacterial populations didn't work together and have this self-sacrifice system in place, this constant, overwhelming pressure from phages could have wiped out that whole kingdom long ago. Instead, somehow, incredibly, bacteria and their phage predators are caught in a kind of balance that produces incredible systems like DRT3 and DRT2 that have helped us completely rebalance our understanding of what it means to be alive in the first place. Sure, the overhype of DRT3 rewriting the rules of life itself is fun if you don't want to pay attention, but the real mechanics of these defense platforms and their place in the anti-phage arsenal are far more interesting. It is a beautiful last stand made by a dying individual to deny resources to the monster about to kill it. The brave last stand at the end of a zombie movie, except it's a real thing that happens in real life billions to trillions of times a day. That's why I love putting the effort into understanding the real details in molecular biology. It's so much more meaningful to see how the base chemical rules of evolution can generate something that looks like altruism even at the single cell level. And it helps me contextualize the weird amalgamation of trillions of cells that I have emerged from. Life just works. That's all it can do. And the more we learn, the more it appears that life works best when we're working together. Either way, that's a good place to put a bow on this. I really appreciate your time. Thanks so much for exploring this with me. And hey, thanks so much for making it to the end of the video. If you liked this, it really helps a lot if you could like, comment, and subscribe to the channel so we can keep establishing a foothold in the wider algorithm. At the same time, I'd love it if you checked us out over at patreon.com/clockworkshow. I'm so proud of how good our paper crafts are becoming, and I'd love to send them to as many people as possible. Additionally, another big help is signing up for our email list over at watchclockwork.com. But hey, let's be real. You've already done the most impactful thing you could by making it to the point where you're hearing these words specifically. And what I mean is just watching the video all the way through. If there's a creator you really like, making sure you watch a video stem to stern is honestly the best possible way you can support them in the current meta. Now, this was kind of a breaking news situation, so I tried to shoehorn this video in before the one that was actually planned, so we haven't seen any payoff to the question I asked y'all in the last video. That said, what's your favorite pepper? I just want to get a quick temperature check from y'all here. Either way, that's a good spot to close out. Thanks for being here with me right in this moment. I really appreciate your time, and as always, I like to leave you with peace, love, and open reading frames. Everyone be well. Thank you so much. Joke's on you, loser. I'll steal my own stuff and build a bomb out of nonsense.